Uh, Dear participant, welcome to the 31st session of Day 4 WADLA 3.0 on topic recent trends in deep learning. So today we have with us Professor Matloob Khusi from Brunel University, London, UK. So he is going to talk about like medical image analysis. So before his talk, so I would like to introduce Professor Matloob Khusi. So, Matloob Khusi has over 2 decades of industry and academia experience. He completed his PhD in AI and data science from the University of Sydney, Australia, in which he developed novel algorithms for understanding big geomic data. Dr. Khusi has earned various awards for his research achievements and has authored more than 75 research papers. During his postdoc at the Children Medical Research Institute, Australia, he developed automated AI-based algorithms for dating the drug discovery process. He has also developed solutions for the financial industry, such as uh, portfolio management, prediction of stock, forex, and commodities market. Recently, he won the UKRI NEC grant. So Dr. Khusi has supervised 6 PhD to completion and more than 100 postgraduate dissertations in various domains of AI and data mining, and is always willing to supervise very talented PhD candidates. So once again, thank you very much, Professor Matloob Khusi, for joining this session. Now the session is over to you.
Thank you very much, Rakesh, for a very comprehensive introduction. As Rakesh mentioned, my main affiliations nowadays with the Brunel University, but I also has an affiliation and very long relationship with some of the other world's top university, including Sydney University and Southampton University in UK and the Solid University. And today's topic, I'm going to talk about how to do medical image, specifically medical image analysis. And my focus is mainly on medical images. But before I get into my real area of topic, I just quickly kind of showcase you a couple of slides just to show you that what I've been else doing, and I also give you a couple of examples, and then we get into the real topic. So this one is kind of advertisement just to let you know, other than the image analysis, what else I do. And if somebody is interested in this sort of work, we happy to take them on board. Rakesh and I've been talking on developing some sort of smart watches. And one of my PhD student who recently finished, we developed a prototype for a blood pressure estimation, and it's a smartwatch. So and NLP also do a lot of work in NLP. In fintech industry, we developed quite a novel loss functions that manage portfolios and balance between lending and borrowing. And finally, I've got a recent PhD student, and we're looking at Web3 and blockchain data, how the money moves between the people rather than traditional banks. And that allows us to predict markets very efficiently. That's the theory. So yeah, if anyone is interested in these kind of projects, getting involved in these projects, you can talk to Dr. Rakesh, and we can set up a meeting and take it from there. So back to our topic of today. So let's look at what the image processing involves, and why do we use the image processing. So you have probably seen some of the examples before. Let me show you a couple of examples that you probably be more aware of. For example, this one, um, diabetic retinopathic severity prediction images are available on Kaggle and other platforms. And you guys, as a computational scientist or machine learning or AI expert, you are required to predict the class of the image, whether there's a no dynamic diabetic retinopathy, or there's a mild or moderate or severe. In this type of image processing is entirely different from the type that I'm going to be more talking about. But this is the one type of work that you usually do. So, and another one is this type of, I'll be more talking about today, uh, this type of image processing, where, for example, in this work, we're looking at whether the nerves are very straight or they are very wiggly or move around, which is an indication of the diseased eye. And you are required to give a number against the twist of these blood nerves. So, or this type of neuroblastoma cancer detection, where we treat cells and then you look at the effect of that treatment. And here's another example in this one, not this one. So let's look at a this is another use case where when I was in the Sydney University working for a Children Medical Research Institute, we were looking at how disease progress and develop on the DNA level, on a molecular level, and this is the telomere. Telomeres are green part of this DNA, and we look at what other proteins and complexes bind at these ends. And on these are microscopic images, and biologists capture them. And our role as a data scientist or image processing expert or whatever you want to call it, uh, to let them know whether there's an effect of the drug on these images. So here's another example where we were looking at the length of the telomere. Telomere, as I said, is the end part of that DNA, and it represents longevity. We can predict how long a person going to live based on the length of these telomeres, and is also a representative of development of many diseases, including about more than 80% of different cancer types. So we looked at how long the telomere is. So we're talking about this sort of image processing rather than, or image analysis, rather than the conventional examples that you probably will look at on Kaggle and other platforms, where you have a fixed classes and you be classifying images. So for these sort of image processing, basically, uh, you are looking at some sort of medical application and you want to do some statistic quantification of these images. Because we can't just say, oh, look at this image, this one looks more red, this one is more green, the thing is more, like you can't, you can explain that thing in the words, but in the scientific community you need to come up with the numbers, how big the effect is, how many more red dots are here than this one, how bright are they. And even if you give throw a numbers, here's a 10 dot, here we have, for example, 2 dots, but is that the difference of the 10 and 2? You can't just say, oh, 10 is way bigger than 2, but is that between 10 and 2, is that difference is significant enough. So for that, you need to do some statistical calculations as well. So you can't apply deep learning all the time and then do the classification, those kind of things that you've been conventionally looking at so far. So, so our focus of this talk is more on the image processing side of thing, and what's the significance of these measurements in relation to the medical applications. So medically, we're looking at the efficacy of the drug. We want to design new drugs, or we're looking at the progression of the disease, or we're looking at the possibility of disease coming back. So these kind of applications you have. Another use case for the drug discovery where we treated the cells, the top one is untreated cancer cell, and then we have on the bottom a are the cells which were treated with various drugs, and these are the pictures from one particular drug. And again, we can't just say, look at this DNA, this is the DNA, this is the mitotic spindle. We can't just say, oh, look at this DNA, this is fat, this is very thin, or here's my algorithm, deep learning algorithm. It can classify um, the drugged image or untreated image. That's not enough. That's not enough for medical application. For medical application, you need to exactly pinpoint what your drug has an effect on your area of interest, on the object of your interest. In this case, in this example, our object of interest is the DNA, what the drug is doing to the DNA, and how the cell reform or compromise when it divides into two. During the cell's divisions, these microtubules develop, and then they cause the DNA to split into two and the cell divides. So, so in these applications, you really want to pinpoint what's happening in the image. The other benefit of this type of image processing, you don't need huge data, and you might not have a huge data to work with. You might have only like maybe 5 images or 10 images. So again, your deep learning based algorithms cannot be implemented here. So in this talk, we're going to be talking about those basics of image processing, and how I hope that will add some value to your knowledge that you are learning part of these lecture series and these workshop series. So very quickly, let's get into the topic. I'm sure all of you are already aware images, most images, color images are formed of three channels: red, green, and blue. So now you need to remember, when we say these three channels, we're talking about these three matrices. So you have a red matrix for the red channel. So basically, these are just a numbers, bunch of numbers, which represent the intensity of this pixel on that particular location. And then for the green channel, again, you have the numbers for the pixel of the green location. It's just a number for the intensity. And when you put these three matrices on top of each other, then that makes a red, green, blue image, a color image, right? So, so in the medical field, you may not have a color image. The microscope that you be working with, it could be just a single channel, grayscale microscope, and you get whatever you get from your collaborator, from your doctors, from your medical experts. So grayscale image is just a single channel image where you have, for each pixel, you just have a intensity of that pixel. Now, many times we convert them into binary image. And why do we do that? Uh, we'll talk about that in a moment. But binary image basically just an image where the value of pixel is either 0 or 1. That's it. So we call it the mask of in the image processing domain, because once when you create that mask, then you can put that mask onto any other image, and then you can identify these are the areas within the mask, and this is our area of interest. We call it region of interest, ROI. You are aware there are various file formats out there, but the basics are similar. I had an example here to convert the file type from one to another. Not a big deal. So usually what we do part of the image processing, we be either enhancing the images, right? Uh, is in that situation, we might want to sharpen the image, sharpen the edges, sharpen our area of interest. We want to increase the brightness of certain parts of the image, which is the area of interest, our region of interest, or we want to remove the noise for the image from the image. So that's our image enhancement. In the restoration type of work, we might want to restore some part of the image which are damaged or which may not be captured appropriately by some sort of error in the microscope. And the image segmentation, where we want to extract exactly the area of our interest. That could be lines, circle, particular shape. So we gonna be doing these kind of things. So many time when you're working with the microscopic images, you have to remove the noise, and there are quite a few famous methods out there. We're gonna look at them now, how to remove the noise. But why we want to remove the noise? Because if we doing some sort of intensity based calculation, intensity could be representative of presence of more disease or more protein in a certain area, right? So when we measure the intensity in a certain location, region of interest in ROI, and if there's a lot of noise in there, so obviously our analysis could be biased because of the presence of this noise. So many times we want to remove that noise, right? Um, and there are a bunch of methods we adopt. We're going to talk about them. So one of the method in removing the noise is very important to understand the binary image and the mask, how we create them, how we apply them. So, so let's look at how we identify the region of interest. In these examples, my region of interest was the DNA and the spindle. Spindle is the cell structure that cause the DNA to split into two, and then the cell division happens. So, to identify uh, particular structures, we apply a number of morphological image processing. And these morphological process involves having a structured element. So it's like a convolutional, in your convolutional neural network, you have learned how you have a filter and you apply that filter onto the images, and then move that small filter around our kernel. You call it kernel or filter, whatever. And then they try to identify an important section or important features present in your image. It's the same thing. Is the same concept actually. So you see the image processing being around for a long time. So that convolutional neural network, the idea was actually adopted from the image processing domain. So it's the same, exactly same concept. So these could be your image, that's your filter or a kernel in the image processing space. We call it structuring element, and then you apply it on your image and then do your processing. So how do you do that processing? You That depends on the method. There are quite a few methods. You could look at the neighborhood. You could do the averages. You could do the means. Uh, in your convolutional neural network, you would have seen there's so many things you can do. And similarly here is the same process. So if we have the structuring element is a kind of straight line, and so then when there are ones available, so it's gonna enhance. If the structuring element is a straight line, so each one get expanded, right? If the structuring element is a vector, is a vertical vector, then your each area will expand downward or upward. So this is a horizontal vector, so it increases the area in the horizontal direction, right? And you do the same on the grayscale images as well, whether it's a number or whether it's a binary 0 1, it does the same thing. So what was the cause of these morphological images when you looked at them, when you visualize them? So the output of this methodology will be um, two types. One is called dilation, another one is called erosion. So in the case of dilation, your small objects will become big because you are applying the structuring element which has more ones than zeros, so it expands. And in the case of erosion, you you remove some of the very small objects, and then your uh, area of interest gets shrunken as well. So is the part of the strategy, is a part of strategy um, get used in so many ways, and one of the common way is the removal noise. So for example, if we wanted to remove mm, noise, and let's say this was a noise, this small object here is a noise, so how do we remove them? So one of the method, there's so many methods, one of the method is erosion. So you reduce, you shrinken your object, so the objects which are very small, they disappear, and then your region of interest also gets shrunken. But then after that, you apply dilution, and then your region of interest becomes bigger again. And in doing that, you got rid of this small noise. Um, so when we doing this kind of operations, whether it's a noise removal or whether we doing the measurement of how big the object is or doing the intensity measurement, we are usually get a choice of these uh, these options, that whether we want to consider the four neighborhood or eight neighborhood. So in many libraries, obviously, you write the code, and many libraries will give you these features. So you need to understand what are these features are. So when we say four neighborhood, that means we only considered pixels upward, downward, left, or right. So you ignore pixels in the diagonal. So for example, if I want to calculate how many of my objects are connected to each other. So if the object is getting connected horizontally or vertically, then I'm only going to count them. Otherwise, I don't count them. So that is called four neighborhood. And for the eight neighborhood, you basically involve all around of your pixel of interest. So even the object is connected on diagonally, you consider them part of the object. Or you can just do the reverse and only um, consider the pixels which are in the diagonal place. And object connectivity, that's again the same. You define mm, which of the object are connected, and you have these choices whether to consider horizontal, vertical, or diagonal. Now let's look at few examples of noise that you will often come across. So in this is one example of salt and pepper noise. Uh, and Salt and pepper noise can usually be easy removed with a median filter. So what the median filter does is, like, you have a structuring element or a window is going around, and then you take the median value of your neighboring element. In this one, for example, if this was a 16, this was a 14, and this one also 40, so maybe then your median is 14 here, and your 16 will get reduced. So and doing whenever you apply these filter, you will always have this choice, whether to consider only the horizontal vertical pixels or include the diagonal one as well. So that's your salt and paper noise. And the other famous noise is a Gaussian noise that follows a Gaussian distribution. And it's these type of noise are usually present in a lots of microscope, but lots of different type of microscope, or even in telescopes as well. There are quite a few different filters that you can apply to remove them and smoothen your image. Two filters are most famous in this space. One is adaptive filter, and another one is veneer filter. So as I said, you can apply many filters to remove the noise. So first thing, to identify whether the noise is present. And who's gonna tell you that? By looking at the images, you can see there's a noise available there. Biologist will tell you that, and the manufacturer of microscopic of a particular microscope will also tell you that how much noise is present, the likelihood of presence of the noise, and what type of noise usually get in the way in their uh, microscopes, right? So another thing that you usually uh, come across is adjusting your dynamic range. So the range of your pixels in your images, and look at this one, these images, on the far left, we can hardly see what's happening here. It's the same image. um, so everything is very black and only the few areas are a little bit bright. In this one we have again very dark area, very sharpened area, but it's very hard to see the object of interest. Here we again in this one, you have a very high dynamic range, but the image is not very beautiful. It's, it's not possible to see the detail of the hairs and some of the other details of the clothes and some other objects. But once you adjust the dynamic range, now you can nicely see that what are the details of hair and clothes and lots of other things. Now, now in is now it's gonna be very domain specific. What exactly this means? Whether you want to just have the image look visually good, or your purpose was to do the quantification. If you were doing some sort of quantification, then you may not need to do that dynamic range adjustment, because you could have 100 of images, and all you wanted to do to quantify uh, some part of the images and also some other parts of the images. If you were doing the quantification or looking at the statistical difference between the one application of the drug and the other application drug, then most probably you will not have to adjust these dynamic range. But if you're showing that in your manuscript, in your article, in your presentations, then you do that adjustment to visually show the feature. For example, so all of these images, they are real image, but I have adjusted their dynamic range to make them visible to you guys. And when even these images, they were not like that. And when I was doing my all of the analysis and the work that's been presented in this paper, uh, none of these images were processed and were adjusted for the dynamic range. But when I'm showing them here and in the manuscript, so I have adjusted the dynamic range so that our audience can see what's happening. Otherwise, these images were not visible at all. Features were available in this. Features were present, and computationally we can see the difference, because we wanted to analyze the raw data instead of after the processing. So for that statistical comparison, you may not need to adjust the dynamic range, but for the viewing and showing that on your slides or in your in your manuscript, or even to the people who want to visually see what's the difference. Okay, we have established the statistical difference. Now let's see what this difference look like to the humans, and that's when you adjust this dynamic range. Another thing that you will usually come across in medical images are point spread function convolution. And as the name suggests, the convolution is the same thing that you have seen in the deep learning convolutional space. It's a kind of noise that get embedded in your object. And this is a spread function that you will be given by your biologist, and the biologist will be given this function by the microscope manufacturer. Every microscope in the world has a limitation, that how small an object can be looked at sharply, and what's the how well it can define its boundaries. It's the same thing. For example, if you have a bathroom scale to measure your weight, you know, so you can measure very easily different people. Somebody is 70 kilogram, another one is a 80 kilogram, and it also tells you in the grams. Usually it has a, like 80.5, but what can't it tell you how much is the difference in milligram? It can't measure in the milligrams. To measure something in the milligrams, you need to have a different type of scale, right? So it's the same thing. Every microscope has a limitation. What's the minimum object it can capture? That nanometer or micrometer. And after, if the object is even smaller than that, then the point spread function will make it look like blurred. And in order to calculate the exact boundaries of your object, so microscope will show you an object like that, object on your right side. Boundaries will be a little bit blurred. So this is going in a very, very high resolution on a very, very low level. Now to calculate the exact boundaries of the object, then you will subtract this point subtract function from here, and then you will be have the boundaries of your object of interest. Because okay, here's a, example of deconvolution. Once your image is convoluted by this, or your image could be convoluted by many other things, so you can do the deconvolution process by subtracting that point subtract function. And even your cameras have that, but usually because for the normal photography you not required to do that processing. Our eye cannot see that minor difference, so you usually don't do that. But deconvolution on a higher scale level, cameras automatically do that. Is an example of a very old camera which could be a little bit blurry. There's a noise present, and after some restoration, different filters, the image could look better. And you have seen how they have revived the images from old movies, or when the man stepped on the moon, how they have restored all of those images and videography as well. Okay, now we've look at how do we measure the region of interest, ROI. And there are many methods, and we look at a couple of famous methods. And why is very important to measure the ROI? Because your medical collaborator is interested in that region, so then you must look at that region. For example, I've shown you an example where we were looking at the tortuosities in eye. Tortu- Tortuosity mean if the veins in your eye are wiggly or they are straight. If they are wiggly, how wiggly are they? They give a number against them. Zero point 0.1 to zero point 0.9 if the lines are very, very wiggly, so the numbers could be very high. So they are interested in a certain part of the image, and then they want to look at what's happening to that particular area, and whatever else happening in the image, they're not interested in that. And for example, um, another example, you apply a drug onto the cell, and you know that this drug supposed to act on the DNA. So where's the DNA? DNA is only in the nucleus. So you have snapshotted your cells. So which area you're interested in looking at? Part of the nucleus. And what's happening to the DNA exactly, So whatever else happening in the cell, you're not interested in that. You're interested in only the section which has captured the nucleus and the DNA, right? So how do you? So one famous method is the thresholding. We do that all the time. Thresholding, very simple concept. You have a grayscale image. Your intensity is from 0 to 255. Usually, the microscope images have a very large intensity scale. Sometimes that could be from 0 to 100,000, for example. Many times we reduce that scale. Sometimes we don't, but many times to make it easier and faster processing, we reduce that scale to 0 and 255, which is the most common scale in most of the uh, um, RGB and grayscale images. So if your image is from 0 to 255, you come up with a number, and after that number you say is 1, before that number you say is 0, right? So if the grayscale image is xy, um, then you can say for this image, if a value is value of each pixel is higher than the certain intensity, then it's 1, otherwise it's 0, right? Let's say we came up with the number 100. So any value of the pixel higher than the 100, that's 1. Any pixel that is lower than the 100, that's 0. Simple thresholding. But then now, how to come up with this number? There's a method. Again, there are various methods out there. One of the famous method is looking at the histogram of the pixel intensity. So you draw your uh, image as a histogram, right? So on your x-axis you have intensity, and on the y-axis you have a count. For example, if this represents a number, let's say it's a 50, so it means you have that many counts of pixels with the intensity 50. Now you can generate the histogram from an image, but you cannot generate an image from the histogram. Uh, here are three images. All of them have exactly the same histogram. So as you can see, the image look very different. All of them have a 50% gray area, 50% white area, right? But you can see the images are entirely different. So the histogram has no way representation of what the image look like. But now this histogram gives a very clear boundary. We can see there's a there's a bell-shaped curve here in the beginning, and there's another spike in bell-shaped, and here's the crest, here's the valley. So that valley clearly giving us a boundary for this type of pixel and this type of pixel. So our boundary right, like, so we can pick up in any one number in between this space, right? So yeah, ideally, in practice, your image will not look exactly the same where you have no pixels in the middle. Practically, it would be more like that, a wavy kind of form, good pixels, number of pixels going up, coming down, 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 and then a veil valley, and then your. So usually we can identify the um, peak for our object of interest. So we can then say anything before this is our background. So make it 0 or make it disappear. And even after that, we can say that, okay, from this one, maybe maybe after this is also, we're not interested in this one either, right? So we can even do a multiple division, so our area of interest could be just right here. But yeah, histogram is a very good indication of how the intensity spread happening in a particular image. So now let's look at another image. Um, here's an example, another example. This is our original image, and we here's an histogram of the image. So in this, um, our object of interest is these rectangles. For example, we want to separate these rectangles. Now, the problem here in this type of um, images, and we will have these type of images in our analysis. We will come across them, that if you apply a single global threshold, then what's gonna happen? Your uh, oh, sorry, I think did I? Oh, I pressed something wrong. Uh, Sorry, I jumped on another slide. Yeah. Okay. So if you apply a single threshold, for example, in this example, if I apply 128, so I can only see the part of one of my region of interest. I cannot see the full rectangles. Uh, so, so in these type of images, which you will very often come across, you cannot apply a global threshold. Sometime it does work for some type of images, but very often a global threshold of one single number um, doesn't work well for the images. So then what do we do? We apply um, some more thresholding methodology, and one of them is adaptive thresholding, and there are few others famous UTSO thresholding as well. So then you can come up with, because there's a variance, there's a large variance in the background, so we can come up with a window. We can say, like, after every 100 pixels horizontally, we'll have a one number for a threshold, and then from 100 to 200 another number as a thresholding, and then from 200 to 300 another one, and so on and so forth. So for this exact image, so I came up with these numbers. The first one is could be 180 based on this histogram, and then again here our object of interest is this one. So let's come up with anything above 120, and then before that, before 80, you remove them, and another one here for this section is 188, for this section is a 226, and then finally you put these windows back into the original image, and then you can see roughly that all of the rectangles are saved. There are some noise in there which we can get rid of that with the morphological operations easily. So this type of thresholding is an adaptive thresholding, that we adopt a threshold number based on some surroundings, or we can even call it the dynamic thresholding. Is There are a lot of uses for this type of thresholding in all surveillance images that you see, like security cameras and the cameras that used in a drone. They are identifying the objects. Actually, that's what they're doing. They identify the object of interest, and then if they want to pinpoint their location, that's what they do. Remove all the background, make the object as one, and then they can identify using that binary image is location, is height, is width, and maybe the center as well for many operations. Now, another thing you need to be aware of when you will be doing this histogram thresholding, that uh, exposure could be an issue um, in your images. Um, for example, here let's look at these three images. These three images, they looks okay to the when we look at with our normal eyes. Then, but when we look at their thresholding, when we draw their mm, histograms, so they look very different. So in this one, you can see a nice threshold going up and down, and this one as well. But in this image, there's a problem here, which you need to tell your collaborator who might have provided you an image. This image looks perfectly okay to anyone, but it has a fundamental problem here. The problem is there are so many pixels that are going over 255. We don't know how over is going, so we have a cutoff here. So this type of an image is called a saturated or overexposed image, because if there's any object of interest which might have an intensity somewhere up here 300 or something, so we haven't captured it. So that means your image could have lost some of important information. So maybe in this example, let's imagine there might be a plane plane flying in the sky, and that could be an object of interest you want to. But then the way the image being taken, it has washed out all the sky, so you can't see anything in the sky. um, so even the clouds are not very well seen. So for the medical images, similar thing could happen. There could be an area of something getting developed when the cancer develops. So that's the thing you want to spot, where which area is the cancer is developing. And if you have this kind of situation, too many pixels going beyond 255 value, then it's no good. Okay, so in these examples, we were probably should wrap up quickly. In these examples, we were identifying the efficacy of the drug, and we studied the effect of that drug using these all image analysis methodology. And then once you have these numbers, you can apply statistical methods to exactly say that if this effect of a drug is a significant enough to be further looked at. Um, okay, so when you will be working with your medical collaborator, one of the pitfall that you might be pushed into, that you want to see the positive results, And as I said in the beginning, the image processing analysis space is different from your other image classification that you probably will do using the image processing or deep learning, where you have thousands of images of one class, thousands of images for another class, and you do any methodology by hook or crook. You need to come up with the highest accuracy and precision and that kind of stuff. So here, this type of image processing that we discussed today is different. Here we're looking at the efficacy of the drug, you know, and your drug may not have any effect, but you will have a pressure from your collaborator. They want to show the effect, and you will see that there are so many studies being published out there, and everybody's claiming a cure to the disease. Then why do we don't have that many cures available in the market? Because the analysis may be a little bit compromised. So, so whenever you will get an images from your medical expert, so they have a pressure of showing the positivity and some sort of positive results. So you need to be aware of that. This is not a classification problem. You exactly looking at the effect of a drug or a process, and that effect may not be in there, right? So in this paper, um, the author just kind of in a funny way, he said people when they see their result as they expect, they feel like, okay, now I have done the processing correctly. But as but in fact, in a reality, with a lots of image processing experience, you can tweak your images in whatever way that the effect look real. That's the possible, could be still scientific, but that's something you don't want to get into that, just to be aware of. I think that's where we'll stop, and we'll take any question if people have any.
Yeah, thank you very much, sir, for your wonderful session. So I think we have some few questions on the chat box, sir.
Yeah, please go ahead.
Chat box, sir. Should I read it, sir?
Okay, yeah, if you can read it for me, that'd be easier. Or let me just a second. I'll switch to. If I stop share, maybe that might be easier for me to see the chat box. Uh, okay. Right. So I'll just go from the top to bottom. Is intensity normalization impact on performance of segmentation? If answer is yes, which normalization method is best to brain MRI images? When we say the segmentation, then our main purpose is to identify the area of interest, right? So uh, definitely your industry normalization or any methodology will affect the segmentation. So we visually and with the help of the medical collaborator, we know that this is our area of interest. And for the segmentation part, we are allowed to do any type of processing just to identify the area, because our focus is just to identify the area um, uh, which is medically relevant, and then you do your processing. Then you can apply that ROI even onto the original images, right? And then you can extract your rest of the pixels from your original image. And then the second part of your question is which method apply works well for the MRI images. That depends on the exact MRI images. We as a human, we are very good when there's a we we, after so many years of training, the medical professionals can see that the different intensity scale in the images does not really affect their judgment. So they can see that, oh, this is a little bit low scale, low dose MRI images, this is high one. But for the computational algorithm, they will fall apart. So you will have to do some sort of normalization all the time. And there could be some noise in your images as well. So it's a trial and error thing. Probably, it'd be hard for me to say that this exact method of normalization will be best for race. You might be able to do some, and then again, if it's a segmentation, the the, the purpose is just to segment that, or the purpose is to classify that. There are different things that you need to identify first, that you want to segment, and why do you want to segment, what exactly you want to do the downstream in your downstream analysis. It's a trial and error thing. You can look at a Gaussian filter, veneer filter. I mentioned few methodology in the adaptive filtering. You can try that and see which one works best for your images. So the next question is, some biomedical dataset faced high class imbalance dataset with tiny lesions. Some research tried to solve this problem by improving loss function during the training in the deep learning. Yeah, that's one of the methods, Anita. You mentioned that people try to adjust a loss function to address the imbalances in this class. So that's one route. Another route is you, and that's an also very famous route, that you generate more of your synthetic data, which looks similar to your low class data set. For example, your cancer images could be only, let's say, 200, and the normal people could be 10,000. Now your algorithm might want to classify everybody a normal person, but you can generate, you can learn the features of those few hundred diseased images and generate more similar images using various methodologies. One of them is GAN. You can generate similar images. Another method is you just do some apply some sort of filtering, then you generate the images, move them around. You do some sort of augmentation. If you just Google augmentation methodology, there's so many. You do skewness, so you do skewness in the image. There's so many methods. So these are the two ways you can address. One is, you mentioned, you introduce some loss function, and then also generate more data. Okay, as Small mentioned, different type was a different type of noise
Technique.
used in the medical image. So we looked at salt and paper noise, Gaussian noise. So these are the most commonly um, noise that are present in the images. When normal cell, okay, so Anita again, when normal cell intensity is similar with abnormal cell intensity, in this case, which approach how? Yeah, so that's very much again depends on what area you want to segment that. Uh, for the images that I was working with, some of the examples I showed you, um, our um, one of the problem I came across, that we had a very different background noise available. Then you try different methodology to remove those noise, and then sometime in some of the experiments, that your area of interest got to be somewhere in the center, because when they take the microscope, they want to have their area of interest right within the center. So you can define an area that anything touching my middle part or this certain area, then I'll consider them part of my ROI. And anything connected to that ROI, I will have them included into my ROI. So these various methodologies you can apply to identify your ROI. Okay, Aditi asks, what we use most standardization or normalization to scale data in deep learning? What do you mean by scale? So normalization scale is probably you're talking about the classification here, Aditi. That when we're doing the classification, we normalization is a very famous thing that you do. You can do normalization beforehand, before image being fed into the neural network. You have it now normalized. And the other type of normalization you have as a layer normalization, and the image get normalized when it gets to that particular layer, or you can do a mix and match of those things. So my favorite one is the image should be standardized before going into the neural network. But then but having a different layer normalization, they also help definitely. Okay, so which method should be appropriate noise remover for the so we discussed that the is very much depends on the type of noise. Um, Sometime you've been told by the microscope experts, the equipment, whatever being equipment being used to generate those images, so they know that these equipment will have this type of noise in there. Point spread function is the one thing that we discussed. That's a type of noise. So then you have to deal with that, and they usually provide you some help with the methods that you should apply to get rid of those. The other type of noise is we looked at the Gaussian noise, sandpaper noise. So this kind of noise also very common in these images. Um, we so the next question is some more technique. Can we apply some more techniques to overcome imbalance issue in a medical image data set? Uh, depends. Depends how are you doing the classification. If if you're extracting the features, one of the features could be bags of words in from your images. Then yes, after that you can apply the smart methodology to generate similar more data set. um, and then but it's that's not a famous method. And I've got to must say that I haven't tried it in medical images. I usually, but I'm not against it. I haven't tried it, but you can try this method, and I can tell you the way you should try doing it. For the medical images, the usual method is generate more images beforehand, not using small. There are various methods using GAN or skewness, generate more images, similar images, and then you use your deep learning algorithm. The way I think the smart, if you want to use it, you extract the features from your image and then apply smart on those features, and then you will have a lots of more features. Then you fed them into, either you save them as a separate data set and then do your training on top of it, um, um, or you just have that done on the fly and then feed into your neural network. But if you do the smart on the raw images, I don't think it's gonna work. I haven't tried it, but my feeling is it's not gonna work. It doesn't sound appropriate. But then after extracting the feature, smoting on that exact features sounds promising. Sounds right. So could be doable. Is it possible to tackle challenges related to domain discrepancy by applying image processing techniques to both the source and target data? I didn't fully understand the question. Domain discrepancy by applying image processing. What do you mean by domain discrepancy? By applying image processing. I don't really understand the question, but if the person is on the call, they can explain it, or I probably already would have run over time. If Rakesh is there, Rakesh, do we have a few more minutes, or we need to cut off here?
Yeah, we can have, sir.
Okay. So if the Sapna is on the call, she can explain what does she mean by domain discrepancy. She can give an example, then probably I might be able to explain. Okay, so she might not be there. That's fine. Any final question? If not, I thank you to Rakesh for inviting me and everybody else for listening. Um, I hope you would have learned something new um, in this subject.
So, thank you very much once again, Professor Matloob. So, really, your talk was very informative. So, our participant has got a lot of insight from the medical domain analysis, means how practically the developed deep learning approaches can be applied for the medical field. So, of course, like if they have further any doubts or they want to have some kind of collaboration in terms of industry or in something, so they would reach out to you.
All right. Thank you, guys.
Thank you. Thank you
Have
very
a
much,
good
sir,
one.
once again.